Hello. Our VIP project was about airfoil validation. And this was done by Isaac Martin, Ian Kwan, Max Lee, Dan Spleen, and Jasper Hawkwam. And myself, Akshay Gadani, am presenting. So our objective was to validate the use of an airfoil for Purdue AMP. We did research. We wanted to research the uses of airfoils and understand the application to the AMP car. We did research on fluid drag and downforce theories to understand limitations. We wanted to apply understanding of fluid dynamics to the airfoil design, and we wanted to run simulations to test and understand the theory behind the foil. For research, we did research on the use of the airfoil, and we found that it basically deflects force due to air resistance upwards. This results in a generation of downforce at the rear of the car, keeping the car planted on the ground and giving those wheels enough traction to really drive the car forward. Limitations, depending on the angle of the air force afflicting vehicle, the airfoil may create drag, and this applies to fixed airfoils, and it adds weight to the car, which slows it down, which in a race, we kind of want to be faster. The principles of automotive airfoil. This is utilizing Bernoulli's principle to generate downforce. Fast moving air creates area of low air pressure, and low air pressure creates force. And as you can see by this diagram over here, low pressure below the wing creates downforce, high pressure above the wing basically pushes the wing down, and because the wing's attached to the car, it pushes the whole rear of the car down. We ran a CFD analysis. We utilized computational fluid dynamics to visually change the velocity of air particles, and the program we used was Fluent and ANSYS Workbench. These are our results. So using the program, we were able to determine that the airfoil model would produce 1,401 newtons of downforce at 40 miles an hour. And this translates to about 10 pounds of force. This amount of downforce validates the AMP team uses use of an airfoil. You can kind of see by the picture here, these are kind of just the air velocities, air particles kind of moving along, and you can see the change in direction as it hits our airfoil. And these are the kind of velocities. In diffusion, anything moving through air will create turbulence. So this wing keeps air relatively smooth. We can kind of see that with how, sorry, I forget the word, but we could see how kind of just smooth overall the air around the airfoil is coming out of the foil. Understanding the pressure gradient, our goal was to have a high pressure above the wing and low pressure beneath. And you could see that the conditions for downforce are met here. We have the pressure is very high on the top, and we have a lower pressure kind of below the airfoil. And that's kind of creating our pressure. That pressure differential is 1 kilopascal, and that's enough to generate downforce. We need to conduct further study to get more calculations and tests to see how the wing information translates to go-kart performance. Additional test velocities need to be analyzed to get a downforce map of the wing. Additional calculations to determine the practical downforce value. And that's it. Thank you.